Nuclear reactions involve changes in the nucleus of atoms, resulting in the release of enormous amounts of energy. There are two main types of nuclear reactions: fission and fusion. Let's take a closer look at nuclear fission. In nuclear fission, a neutron bombards a heavy atom like uranium-235. When the neutron strikes the uranium nucleus, the nucleus becomes unstable and splits into two smaller nuclei. This process releases energy, radiation, and additional neutrons. These released neutrons can trigger more fission events, creating a chain reaction. The chain reaction starts with a single fission event. Each new fission releases more neutrons, triggering multiple reactions. Now let's examine nuclear fusion, which is a different type of nuclear reaction. In nuclear fusion, lightweight nuclei such as hydrogen isotopes combine under extreme temperature and pressure. When the nuclei overcome their electrostatic repulsion and get close enough, they fuse to form a heavier element like helium. This fusion process releases even more energy than fission, making it an incredibly powerful reaction. Comparing the energy output, fusion reactions can produce 3 to 4 times more energy per reaction than fission. To summarize what we've learned about nuclear reactions, these nuclear reaction principles form the foundation of nuclear power generation. Let's explore how nuclear power plants convert nuclear reactions into electricity. The core component of a nuclear power plant is the reactor, where controlled nuclear fission occurs. Fuel rods containing enriched uranium are arranged in the reactor core. These rods contain the fissionable material that undergoes nuclear reactions. Control rods made of neutron-absorbing materials like boron or cadmium regulate the reaction rate. By inserting or withdrawing these rods, operators can control how many neutrons are available for fission. Water circulates through the reactor, serving two crucial functions: as a coolant to remove heat, and as a moderator to slow down neutrons, which makes fission more likely. The heat generated by nuclear fission is transferred to water in a closed primary loop. This hot water then flows to a steam generator, where it heats water in a separate secondary loop, creating steam without mixing the water circuits. The steam drives turbines connected to generators, converting thermal energy to mechanical energy and then to electrical energy. The high-pressure steam turns the turbine blades, spinning a shaft connected to the generator. Here's the complete nuclear power plant cycle. Nuclear fission in the reactor creates heat, which is transferred by the primary coolant loop to the steam generator. The steam drives the turbine, which spins the generator to produce electricity. The water in the primary loop is kept under high pressure to prevent boiling, while water in the separate secondary loop is converted to steam to protect the environment from potential radioactive contamination. Nuclear power plants incorporate multiple safety systems. The containment building is a reinforced structure designed to prevent radiation leaks, even in worst-case scenarios. Emergency cooling systems can flood the reactor with water to prevent overheating. The control room monitors all plant operations, and backup generators ensure safety systems remain operational even during power outages. This completes our exploration of nuclear power plant operation, where the energy released from splitting atoms is harnessed to generate electricity that powers our world.